Differentials and linear approximations. In this section, we'll introduce a new topic called the differential. That can be used in some application, but will become really important later on when we learn about antiderivatives and the integral. And then we'll talk about a concept of linear approximations. And really, this is something we sort of already know how to do. It's just a different way of looking at it. So first, differentials. Right, so we say a differential is like this. If we're given some function, given y as a function of x, we call dy and dx the differentials. All right, so if y is a function of x, then dy dx, right? Notice that's the differential notation. Dy dx is equal to f prime of x. So if we rearrange this a little bit, we say that dy is f prime of x dx. This doesn't seem like much, but will become important later. So let's consider an example here. If y is 9x squared plus 7x minus 3, find the differential. All right, so recall our definition. We said that dy is f prime of x dx. So then dy is 18x plus 7 dx. That's the differential. Now, you might say, well, wait, shouldn't there be two differentials, dy and dx? Generally speaking, we call the differential this statement, dy equals f prime of x dx. All right, so now let's see how we can use the differential. So if y is, so given that same setup, compute delta y and dy if x changes from 1 to 1.05. All right, so then delta y, the change in y, would be the function evaluated at 1.05 minus the function evaluated at 1. So according to my calculations, then delta y is 14.2725 minus, and then f of 1 is 13. And so then the delta y is 1.2725. So as x changes from 1 to 1.05, then, so the delta x is 0.05, and the delta y is 1.2725. Now what about the dy? Well, the dy, well, this is a little trickier. So what we're saying is we're letting x equal 1, let x equal 1, and let the dx, let the change in x be 0.05. So then dy would be f prime of x, so that would be 18 times 1 plus 7, and then the dy times 0.05. So that would be 25 times 0.05. And 25 times 0.05 is 1.25. And notice that those are relatively close to each other. But in a manner of speaking, or one way to think about it is that dy was easier to calculate than the delta y. We didn't have to go through the function twice and then subtract. Instead, we used the derivative of the function and the change in x to calculate the dy, and these are relatively close to each other. It's a pretty good approximation. The dy, so note that the dy is a good approximation of delta y. All right, and for practice, this would be a good time to pause. If u is 3 tangent theta, find the differential. So if u is 3 tangent theta, these are just different variables. So we just use the different variables. If u is 3 tangent theta, then du is 3 secant squared theta d theta. That's the differential. And again, this concept of the differential is going to be really important when we learn about antiderivatives and what's called the substitution method for calculating antiderivatives. Let's see another place where differentials can be used. So here we're told that the sides of a cube are found to be 53.4 centimeters in length with a possible error of no more than 0.1 centimeters. What is the maximum possible error in the surface area of the cube? So here we have a possible error in measurement. How does that change some other value that's based on that measurement? And it turns out that we can use the concept of differentials to answer this problem. All right, so I know that the surface area of a cube is 6 times the side square, right? A cube has 6 sides, and each side has an area of the side, the measure of the side squared. All right, so now we have the side. We know S to be 53.4 centimeters with a possible change in S, right? With ds equal to 0.1 centimeter. What's the possible error? What's the change? What's the possible change in the surface area? So calculate the differential. So then dSA, the change in the surface area, dSA is equal to 12S ds. So then dSA would be 12 times 53.4 times ds times 0.1. So calculating that, 12 times 53.4 times 0.1. So dSA is 64.08, and this would be in the change in the surface area. That would be in square centimeters. So a small change in our measurement of the length of the side can result in a fairly large change in the surface area. Our second major topic for this session is linear approximations. And this is, again, something that I mentioned earlier, something that we sort of know already. We know how to do this. We just haven't thought of it like this. So here I've got a generic graph of a function. And the idea is, well, what if I was to consider, some point A, some x value A, and the idea is, well, then on the curve near that point A, if I was to want to approximate the curve near that point A, what I could do is, instead of thinking of the actual curve, why don't I think of the line that approximates that curve right there? Why don't I think of the tangent line to the curve at that point? As long as I stay near that point A, the tangent line to the curve at A should be a reasonable approximation of the curve. All right, so that's the big idea. The tangent line to a curve at x equals A approximates the curve near x equals A. All right, so near, what does near mean? Well, that's a little tricky, but as long as we're reasonably close, then the tangent line should be a good approximation of the curve. So let's see an example of that. Let h of z be equal to the natural log of z squared plus 5. We're asked to find the linear approximation to h of z at z equals 2 and use the linear approximation to approximate h of 2.1 and then compare that to the actual value of h of 2.1. All right, so part A. Let's find the linear approximation. Well, a general formula, right, is that, well, I suppose we could probably do that on the previous slide. Let's go back for a moment. So if this is A, right, here's this A, we have the point A, f of A, and we know that the slope m would be f prime at A, assuming it exists. So then the linear approximation, right, the linear approximation is given by, well then, let's just call it L of x minus f of A is equal to f prime of A times x minus A. So this is just the point slope form of the equation of the line, where I'm using L of x instead of y. So then L of x, the linear approximation, is f prime at A times x minus A plus f of A. And here's a general form that you can use to find the linear approximation. It's just the tangent line at the point A, f of A with slope f prime of A. All right, so it's nothing new, just a different way to look at it. All right, so let's go back to this exercise. Find the linear approximation to h of z at z equals 2. All right, so at z equals 2, we have the point, so then f of 2 would be the natural log of 9. And we can calculate that. Let's see, the natural log of 9 is 2.197. All right, so then and f prime of 2 would be, let's see, to find the derivative, let's find the derivative more generally first. F prime of z is, all right, so f prime of z would be 1 over z squared plus 5 times 2z from the chain rule. So then f prime of 2 would be 1 over 9 times 4, so 4/9. So then the linear approximation would be L of z minus 2.197 is equal to 4/9 of z minus 2. So that would be 4/9 z minus 8/9 plus 2.197. Let's approximate this. So 4/9 is approximately 0.45, I think. Let's see, 4 over 9. Oh, 0.44. So let's just say 0.44 z, and then minus 8/9 plus 2.197. Actually, you know what? We're going to leave it. I'm going to go back a couple steps. And there's a good reason. We're going to leave it like this. So then L of z is 4/9 of z minus 2 plus 2.197. And I'm going to leave it like that. I'm not going to distribute. I'm not going to put it in the slope-intercept form. And there's a good reason for this. Remember that this is only useful, this linearization is only useful near z equals 2. So we're going to be substituting a number near z equals 2, and so then subtracting 2 in a sense gives us just the change. And don't worry, it'll make sense in a moment why I made this, why I left it like this. All right, so then B, use the linear approximation to approximate h of 2.1. So then h of 2.1 is approximated by the linearization at 2.1, which is then equal to 4/9 of 2.1 minus 2 plus 2.197. And so notice 2.1 minus 2, that's 0.1, so 4/9 times 0.1, that's easy enough to do, plus 2.197. All right, so 4/9 times 0.1 plus 2.197 is 2.241 approximately. All right, so now it says, now compare this to the actual value of h of 2.1. So part C, h of 2.1 is equal to the natural log of 2.1 squared plus 5. And so then 2.1 squared plus 5, and then the natural log of that is 2.242 to 3 decimal places. And so what we can see is this is a pretty good approximation. It's off by 1/1000th. And let's see why this is, let's sort of see why this is happening. I'm going to go over to Desmos. Let's go over to Desmos and let's graph, I'm going to use x instead. Let's graph y equals the natural log of x squared plus 5. So there's the graph of this function, and what I'm going to do is I'm going to zoom in on x equals 2. I'm going to zoom in near x equals 2. And notice what's happening as I zoom in. Notice it appears to almost be flat near near x equals 2. And in fact, after zooming in a while, notice this looks pretty much like a line. So now let's go over, let me bring up that line. The line was 4/9 of z minus 2 plus 2.197. 4/9, let's graph 4/9 of x minus 2 plus 2.197. And notice that near z equals 2, it is almost exactly the same as the line. In fact, they're almost indistinguishable near z equals 2. And so at 2.1, which is here, right, on this scale, here's 2.1. Notice that they're almost indistinguishable between the red and you can't even see the blue. So again, this is what a linear approximation does. It gives us a line that approximates a curve. But again, it only approximates the curve near that point. If we zoom back out, see, notice there's the line in blue, and at x equals 2, it's a good approximation. But then once we go too far away, once we get out, I don't know, more than a unit away from 2, it's no longer a good approximation. So a linear approximation is very good nearby, as long as the derivative is nice. As long as the function doesn't change, doesn't jar too much. All right, so let's go back to, let's look at another example. Find the linear approximation to sine x at x equals 0. Now would be a great time to pause. Try this one out on your own. So this is actually a really important approximation in physics. There are many times where instead of using the actual function sine x, in physics you will use its linear approximation. As long as we assume the change in the angle isn't too much, this approximation is going to be a very good approximation. Alright, so we know that at x equals 0, f of 0 would be sine of 0. Sine of 0 is 0. F prime of x is cosine x, and f prime at 0 is 1. So then the linear approximation to sine x at 0 would be, the linear approximation would be 1 times x minus 0 plus 0. The linear approximation is simply x. So sine x near the origin behaves like x. Let's see that graphically. Again, here's Desmos. Let's graph sine x. There's sine x. And let's graph x. And let's zoom in on x equals 0. And notice how that blue line is a very good approximation of the curve within, a small angle. I don't know, it looks pretty good between negative 0.3 and 0.3. Now, outside of that, it's still a decent approximation until about 0.5 on either side. And then after that, they start, moving apart from each other. But if we have a small angle, sine x can be reasonably approximated with just x. And that becomes so important in physics. Without using a root or exponent button on your calculator, approximate the fifth root of 33. Now I want you to think about this for a moment, and maybe try this, and here's a hint. You can use a linear approximation to do this. So here's what I'm going to do. Let's call the function the fifth root of x. Now I know that f of 32, I know the fifth root of 32 is 2. And I know that the derivative is 1/5 x to the negative 4/5. So then f prime at 2 would be 1/5 times 2 to the negative 4/5. F prime, I don't want f prime at 2, I want f prime at 32. So that would be 1/5, let's fix this. F prime at 32 would be 1/5 times 32 to the negative 4/5. So that's 1/5 times 1 over, how do we want to do this? Let's do this as the fifth root of 32 to the fourth power. Fifth root of 32 is 2. 2 to the fourth is 16. So that's 1/5 times 1/16. That's 1/80th. So near x equals 32, then a linearization of the linearization would be 1/80th by x minus 32 plus 2. And so then f of 33, which is the fifth root of 33, is approximated by the linearization at 33. And so that would be 1/80th times 33 minus 32 plus 2. And so that would be 1/80th times 1 plus 2. And so that would be 2 plus 1/80th, 2 and 1/80th. is 161 over 80. And 161 over 80 is 2.0125. Now, if we were to just use the root or calculator, the appropriate button on our calculator, the fifth root of 33 is 2.01234617. And so this is accurate to within 3 decimal places. It's only off in the 4th decimal place. So this is actually a pretty good approximation. At least, this approximation is pretty good near 32. And so, before calculators were a thing, people actually used to do this to approximate roots or various exponentials or some other situations before the invention of, say, a slide rule or then calculators. So this linear approximation, this example isn't so useful anymore, but the idea behind it and approximating functions with a linear approximation is important, and you will see it in later mathematics and physics courses. All right, so that finishes up this topic. All right, have a good one.